question number 9. That's what it says. It says compute the expression like this, and because it is given in the very beginning of the set of questions, we can I imply that we have to compute it with only algebraic methods. I mean, some of you may be aware of like I said, doing operations with complex numbers when they're given in Cartesian form, it's not sometimes they're not the most sometimes they're not the most efficient way to do these operations. Sometimes you can do in the other way, but this time it's a question number 9 in the first part of the tutorial sets. We have to do it in the pure algebraic form. Now, when you first look at a question like this, the first suggestion which comes to my head would be just do the expansion. And when you do the expansion of this when you do the expansion of the sum of two numbers raised to the cube, you normally do this expansion with the help of what is called the binomial formula. For the cube, binomial formula, it's nice. Thank you. Thank you for spotting the typo. Binomial formula, there is a higher version of them. I mean, there's a general way we can produce binomial formula for any powers. We will discuss it actually today in 15 minutes. But for now, just for this question, we need only the cubic version of the binomial formula. And I think cubic version we know without any reference to higher binomial formula or Pascal triangle. Here it is. When you raise the sum of two numbers to cube, basically the expansion looks like this. You cube the first, you triple the product like this, you triple the product like this, and that's your expansion. I hope you remember this expansion anyway, without any high binomial formula, binomial coefficients and things like that. Now, even if you know this formula, if you try to apply this formula directly to expression like this, you will hit lots of not difficulties, but it will be a long computation, because if you do it directly, I just attempted it here. If you do it directly, you have to first cube the first term here, then triple this square of this and the term like this, and then will be lots of other expressions like this. And then when you do the full expansion, then you have to use the binomial formula here again and binomial formula here again, and it will be more binomials further down the road. Directly, it doesn't seem the best way to do it. What I suggest we do, we just rearrange the terms here a little bit differently, like this. I will take this I with this negative. I will do the expansion under my square brackets, and I will rearrange the terms under my square brackets. That's how I will rearrange them. I will take this cube, I will take this square root of 3, and I will combine this with negative I. And then the rest will be combined again together. That's that's my rearrangement. It's not because even after I did this rearrangement, again, if I do the expansion directly, I will hit the same difficulties. Again, I will need to do like a binomial again over this little bracket, and then binomial over this little bracket. It still will be lots of computations. So instead of doing that, instead of expanding this straight away, what I suggest to do next, yes, we can factorize things. We can take this one of these brackets and take it out like this. It may look not so simple so far, but if you find this quotient, like you suggested even a better way to find that quotient, because you just saw it, you have the insight by looking at it. You tell me that the numerator is negative I times the denominator. Is that what you said? Well, when I was presenting this, when I was planning to present this, actually I computed this quotient by the way we compute the quotients of two complex numbers. Here it is. Here's a quotient. I multiply this quotient by the complex conjugates, top and the bottom, you see? Complex conjugate to the denominator, complex conjugate to the denominator. If you do all of the expansions, this is the expansion here, and at the bottom we have sum of the squares of the real part and the imaginary part, which is simply 4. And the whole thing is just I, so it's not negative I, but I. But still it's a great insight, thank you very much. And so the whole thing just reduces down to 2 cubes like this. like I said, knowing the complex numbers, knowing the trigonometric form and the exponential form of complex numbers, it helped me, and I'm sure it helped the students at the back row there, envisage these sort of steps. And yet the presentation itself doesn't make any reference to that, doesn't it? That's a true skill of knowing the complex numbers. And I hope that by the end of this chapter, some of you will have these kind of skills. Well, the finish of it is easy. So we can use the binomial expansion twice. It's still we need to use it twice, but now only simpler factors. One of them like this and one of them like this. Basically, I just hid most of the tedious computations with dots. I hope you can recover all of those dots, or maybe I even didn't do that. That's the expansion for the first binomial. Cube of the square root of 3 is like this. This term will be looking like this, and the rest is negative 8i. And the binomial expansion for the second factor, again, I just hiding some details. That will be the expansion like this. If you multiply these things, that will be the answer, which is expected in question 9.